Alright, in this video we're looking at line notation used to represent voltaic cells. This is also known as cell notation. It's a shorthand way of describing a voltaic cell rather than drawing and completely labeling a diagram like you might see here. So when you are given an electrochemical cell, a voltaic cell like this one, we have a lead electrode in a 1 molar lead nitrate solution and an aluminum electrode in a 1 molar aluminum nitrate solution. Those two half cells are connected by a salt bridge with some potassium nitrate in it. Because the concentrations of the lead and the aluminum are 1 molar, and because the temperature of the battery is at 25 degrees Celsius, this is considered a standard voltaic cell. So it's under standard conditions. The first thing we want to do when we're given this is to decide which of the two electrodes, which is the two half cells, will be the anode and which will be the cathode. So to decide that, we need to look at a table of reduction potentials, and we're going to find the half reaction, the reduction reaction, where lead 2+, which is in the 1 molar PbNO3 two nitrates are attached. So there's really 1 molar Pb2+ in here. So lead 2+ gets reduced to form lead, and in the other half cell we have 3 nitrates attached to the aluminum, so we know this is 1 molar aluminum 3+. So we want to find the reaction where aluminum 3+ gets reduced to form aluminum metal. So I've got a table here which is very large font, so you can see that rather easily. It's a partial table of reduction potentials. So I'm going to find the half reactions for lead and for aluminum. And here's the lead half reaction. Lead 2+ gets reduced to make lead metal. And the voltage for that, a standard reduction potential, is negative 0.13 volts. Down below, aluminum 3+ gets reduced, and there's a typo there that should say 3 electrons, to make aluminum metal. And for that, the reduction potential is negative 1.66 volts. So we can tell from this that the lead electrode has a higher reduction potential than the aluminum. Because lead has the higher potential, the lead electrode will be our cathode. Reduction occurs at the cathode. So whichever one had the higher reduction potential is going to be where reduction occurs, and that'll be the cathode. Then the aluminum half cell is going to be our anode. The aluminum electrode is the anode, and oxidation is occurring in here. Okay? All right, the reason we wanted to do that is because when you describe the cell using line notation, by convention you always begin with the anode. So the anode will come first in the line notation, followed by the cathode. You can remember that alphabetically, A before C, if that helps. So here we go. This is very simple. We start with the aluminum electrode, solid aluminum electrode. I'm just going to write Al like that. Some people will put the phase beside it, Al solid. And then we're going to draw a vertical line. The vertical is called line notation because we have these lines. A single vertical line like this represents what's called a phase boundary. Okay, a phase boundary. Phase, as in solid, liquid, gas, aqueous. There's a phase boundary because we have a solid aluminum electrode in contact with the aqueous aluminum ions. Solid aluminum, aqueous aluminum, there's a boundary, a phase boundary in between those. So we represent the aqueous aluminum 3+ 1 molar in brackets. If the cell were operating under non-standard conditions, this concentration might not be 1 molar. Coming back to our picture here, so we've gone from the electrode to the aluminum ions floating in the half cell here, and then we're going to travel through the salt bridge to get to the other half cell. In line notation, to represent the salt bridge, we use a double vertical line. Okay, so the double vertical line is your salt bridge. Coming out of the salt bridge on the other side, in the other half cell, we're in our 1 molar lead 2+ aqueous solution. So I'll represent that as Pb2+ 1 molar in brackets. And then that lead solution is in contact with the cathode, the lead electrode over here. And again, it's aqueous lead and solid lead. So we have another phase boundary, a single vertical line. So those single lines are phase boundaries. And on the other side of the phase boundary, the solid lead metal. So when you read the line notation, you don't have to stop and think about it, because whatever comes first will be the anode. So the aluminum gets oxidized to become aluminum 3+. Then the salt bridge, and on the other side of the salt bridge comes the cathode, where lead 2+ is being reduced to form lead metal. Right? That's how you interpret cell notation or line notation. Now the first 3 or 4 examples that I'm going to go through here are useful for chemistry in the regular program, whereas the last few examples, last 2 or 3 examples, you might find also in an AP level course. Alright, so this next example, if you think you know what you're doing, you can pause the video and try it yourself. We want to start by figuring out which one is the anode, which is the cathode, which electrode is which, and then go ahead and draw your line notation. So looking at my table of reduction potentials, we're looking for magnesium with magnesium 2+, Mg2+, 1 molar is floating around here, and we're looking for copper with copper 2+. I can tell the charges because, again, there's 2 nitrates bonded to magnesium, so the magnesium is 2 positive, sulfate is 2 negative, and therefore this copper is 2 positive. So find those 2 half reactions on your chart. So looking at this chart here, copper 2+ gets reduced to make copper metal, has a voltage, a reduction potential of positive 0.34 volts, where magnesium 2+ getting reduced to make magnesium is at negative 2.37 volts. So of those 2, the copper has a much higher reduction potential, so the copper in this case will be the cathode. Reduction will occur there. The magnesium will be our anode, where oxidation occurs. Now that I understand that, I can start the line notation. You begin with the magnesium electrode. The anode comes first, so Mg. You draw a phase boundary because the magnesium is immersed in the aqueous magnesium 2+ solution, so Mg2+. I'll put its concentration, 1 molar. We have a salt bridge that takes us to the next half cell. On the other side of that salt bridge, we're in the 1 molar copper 2+ solution, so Cu2+, 1 molar. And then that copper solution is in contact with solid copper, another phase boundary, and the solid copper metal is our cathode. So there's the line notation that represents this voltaic cell. All right, so try this next one. Very similar. Pause the video if you think you understand this now, and see if you can do this yourself. All right, for this one I'm going to have to revert to a different reduction potentials table, because the one I had there doesn't have the gold half reaction. So I'm looking for a half reaction between gold metal and gold 3+, Au3+, being reduced to make gold metal, and Fe2+ getting reduced to make Fe. So I've got a slightly more involved reduction potentials table here from our data booklet in chemistry. And up here is the gold 3+ being reduced to make gold. It's got a very high reduction potential. And the other half reaction between Fe2+ and Fe is way down here. Fe2+ gets reduced to make Fe with a much smaller reduction potential. So the gold had the higher reduction potential, so gold will be our cathode. Reduction will occur here. The iron will be the anode, and oxidation will occur there. So now this is relatively simple. We begin with the anode, Fe, the iron electrode, a phase boundary because it's immersed in the Fe2+ solution. It's a standard cell, so the concentration is 1 molar. We go through a salt bridge. On the other side of our salt bridge, we're coming into the gold 3+ solution, 1 molar. This would be a very expensive voltaic cell. So 1 molar gold, and that gold solution has a gold metal strip as the cathode, so there's another phase boundary, and then we have solid gold metal as the cathode. So the anode comes first, and then the cathode next. All right, so those first 3 examples are all very straightforward, simple examples that would easily be used in a regular high school grade 12 chemistry class. Now here is one that's slightly more complicated. In this case, we see on the left a nickel electrode immersed in a 1 molar nickel 2+ solution. But on the right, we have something a little bit more complicated looking. We have a platinum electrode. Now, platinum is an inert electrode. Inert means it's chemically unreactive, so the platinum will not be involved in the chemical reaction that's occurring here. So I'm not going to look up platinum on my reduction potentials chart. Instead, the platinum is immersed in a solution with 3 different things in it. We have 1 molar potassium dichromate, which has dichromate in it. We have 1 molar chromium 3 nitrate with the chromium 3+ ion. And then we have 1 molar strong acid, nitric acid, which will have 1 molar hydrogen ions in it as well. So we have an acidified solution of dichromate and chromium 3+, everything at 1 molar. All right, so now let's go look at our reduction potentials chart. Again, I'm using the one from our data booklet at school. So the left-hand side was the nickel with nickel 2+, and nickel 2+ is down here. Ni2+ gets reduced to make nickel metal with a relatively small reduction potential of negative 0.24 volts. Up above, we see dichromate in an acidified solution with hydrogen ions being reduced to make chromium 3+ and water. And that reaction has a voltage of 1.33 volts. So it's a much higher reduction potential. So that tells me that that dichromate, hydrogen ion, and chromium 3 half cell is going to be the cathode, whereas the nickel half cell will be our anode. The nickel is going to get oxidized when it reacts with the with the dichromate, which is getting reduced. Okay? So coming back down here, then I'm going to write the line notation down below the cell. It's a little bit more involved. So the cathode, the one with the higher reduction potential, was the electrode with the dichromate, had the higher reduction potential. So this is where reduction will occur. The nickel is our anode, and it's where oxidation occurs. So like the other examples, we'll begin with the anode. We have a nickel metal strip. It is immersed in a nickel 2+ solution with a concentration of 1 molar. So this part is just like before. We go through a salt bridge. Now on the other side of the salt bridge, we're in a solution with all 3 of these things in it. Now the 3 things that are of interest here are the dichromate, Cr2O7 2-, the chromium 3+, and those hydrogen ions, which are floating in the water as well. Now when we looked at the half reaction, it was dichromate which was going to react with the nickel, and it had to have hydrogen ions present as well. So I'm going to write dichromate, Cr2O7 2-, 1 molar, comma, hydrogen ions, 1 molar, and then we also have the chromium 3+, 1 molar. All of those are aqueous, so there's no phase boundary between them. But then those three ions are in contact with the solid platinum metal strip. So there will be a phase boundary between the aqueous reactants and products and the electrode, which is solid. So then I just write PT, the solid platinum strip, because you do have to show the electrode as well. So there is a line notation for an electrochemical cell, a voltaic cell, where one of our electrodes had no solid component in the chemical reaction. There was no solid chromium in the reaction. Everything in the reaction was aqueous. So therefore we used a platinum metal strip to conduct the electricity in the voltaic cell. All right. The next example is again a little bit more complicated. It has a gas electrode. Okay, so this one has a gas electrode, chlorine gas, at a pressure of 1 atmosphere, or 101.3 kilopascals, 760 millimeters mercury. You notice those are all standard pressures. We have concentrations in the 2 half cells, 1 molar. So this is all under standard conditions. We'll assume the temperature again is 25 degrees Celsius. Now, one obvious difference besides the gas electrodes, so chlorine gas is bubbling in here, you see the bubbles of gas, is that we don't have two separate beakers connected by a salt bridge. Instead, we have two containers with a porous barrier in between. The porous barrier allows ions to travel through it, which means we don't need a salt bridge, which is essentially does the same thing. So this is another representation of a voltaic cell. So we're going to look up on our reduction potentials chart a reaction between chlorine gas and chloride ions. The 1 molar sodium chloride has chloride ions. Again, because there's nothing there that's solid, there's gaseous chlorine and aqueous chloride, we need to use a solid platinum metal strip, which is inert. Now, sometimes instead of platinum, you'll see carbon being used. Graphite is very commonly used as another inert electrode in these voltaic cells. In the other half cell, we have silver metal strip, and we have 1 molar silver nitrate, which contains 1 molar Ag positive. So we have Ag positive here, we have Cl minus here. So looking up those two half reactions, go back to my larger table here. Up here we see chlorine gas gets reduced to make chloride ions with a reduction potential of 1.36 volts. Silver gets reduced with a potential of 0.8 volts. So chlorine gas has the higher reduction potential. So the chlorine electrode is going to be our cathode, where reduction occurs, and the silver electrode will be our anode, where oxidation occurs. All right, so now we're going to represent this gas electrode using line notation. So the anode comes first, so we write Ag, the silver metal strip, is in contact with the silver ions in solution with a concentration of 1 molarity, standard conditions. Then, although there isn't a salt bridge, we go through the porous barrier. So I'm going to represent that again with a double vertical line. That's the salt bridge, and in this case, the porous barrier that allows the ions to travel across. On the other side of that porous barrier, we have two things. We have chloride ions, and we have the chlorine gas, the Cl2. Now, those are different phases. The chloride ions are aqueous, and the chlorine gas is gaseous. So I'm going to represent it as we're going to need a phase boundary between them. So I'm going to put chlorine gas, because it's the thing that is being reduced at the cathode. So chlorine gas with a pressure of 1 atmosphere, in brackets. And then we'll need a phase boundary, because, again, it's gaseous, and we have chloride ions, which are aqueous, and their concentration is 1 molarity. So those are the two things that are reacting. Chlorine is being reduced to make chloride ions. And then there's another phase boundary because those chloride ions are in contact with the solid platinum metal strip. So we'll put PT solid as the actual cathode electrode. All right, so there's a gaseous electrode with a porous barrier in between them and the line notation that represents it. One last example, this is another gas electrode. We have nitrogen monoxide gas, NO, and it's in a solution with acidified nitrate ions. So there's going to be nitrate ions in here, and there's also going to be hydrogen ions in here. And although it doesn't say it clearly, both of those are going to be at 1 molar concentrations. And the gas is going to be at 1 atmosphere pressure. Now we have, assuming 25 degrees Celsius, we have standard conditions for the cell. The chromium cell, there's a chromium electrode with 1 molar chromium 3+ in that half cell. So let's go to our reductions table. I'm going to use the one from our data booklet again. So I want to find the nitrogen monoxide half reaction. Looking up here we have it, nitrate ions along with hydrogen ions get reduced and they form nitrogen monoxide gas, and the voltage for that is 0.96. Now you might notice that I'm ignoring the water that's also being produced. Water is produced, but the water, of course, in both sides of the Voltaic cell, these are aqueous solutions, so there's lots of water present, so I don't normally show the water in the line notation. So we have nitrate ions with hydrogen ions, the acidified solution, being reduced to make nitrogen monoxide gas, and it's got a reasonably high reduction potential. Down below, we'll find chromium 3+. Here we are, chromium 3+, getting reduced to make chromium metal. It's got a much lower potential. So the nitrates will get reduced as the cathode, and the chromium will get oxidized as the anode. So this is my cathode, where reduction occurs. This is the anode, where oxidation occurs. So we'll use the anode first. So we have the chromium metal strip. It is immersed in the chromium 3+ solution, 1 molar, aqueous. Then we're going to go through our salt bridge. And on the other side of the salt bridge, the nitrate ions and hydrogen ions are being reduced to form the nitrogen monoxide gas. So I'll put the nitrate ions 1 molar, comma, the hydrogen ions 1 molar. Now those are both aqueous, and the nitrogen monoxide is a gas, so we're going to need another phase boundary, aqueous and gas. So NO 1 atmosphere. And then of course there's also the electrode, which again in this example is a platinum strip, PT, which is chemically inert. So another phase boundary, and the electrode is the platinum metal strip.